the leaves branches, they do a 1, 2, 3, 4, I'm sorry, 1, 2, 3, 5, 8, 13, okay? It's called the Fibonacci progression. And that progression is such that if you take any two numbers in the sequence and add them, you get the next one, 1, 2, 3, 5, 8, 13, etc. The point is that that Fibonacci progression, which is perfect branching, perfect nesting, actually leads to the ratio, the golden mean, which is called phi. Often it's symbolized by the Greek letter phi, which is a circle with a vertical line through it. And phi, the golden mean ratio, is the solution to perfect nesting or perfect branching. And we're going to see later that that harmonic ratio actually shows up in the heartbeat as the space between harmonics in the chord, the music of the heart, deciding what chord to play. And when the space between harmonics is a multiple of phi, the golden ratio, it appears people are generally having an emotion that's heart-centered or open or blissful. And so Mother Nature is solving the problem of perfect sharing by solving the problem of perfect branching, which turns out to be the solution to the problem of perfect nesting, which is the solution to perfect compression. So all of these things are related to the golden ratio or the golden mean or the sacred cut. You know, the sarcophagus in the Great Pyramid has that shape, that square, and you have that shape in the Parthenon in Athens, Greece. Okay, so sacred structures use this shape to embed magnetism. Well, it turns out that genetic material is all about that shape, and we'll see some pictures in a minute. So let's go back here now to the magnetic X, and we'll look for that ratio in DNA. So now here we have some pictures of the genetic material. And again, this is the top-down view of the DNA right here. And you can even zoom in on a bit. But it turns out that if you map the way the DNA helix is ratcheted, the golden ratio is the distance between the rungs of the ladder right there, okay? And the golden ratio squared, that's called the vertical increment of turn. The golden ratio, or phi squared right there, is the horizontal increment of turn. And then the radius of the turn, which is this distance from here to here, in angular measure, is golden mean cubed. So length, area, and volume, golden mean squared, and golden mean cubed, are preserved in a ratchet. It's a simple way of saying that no matter how you cook it, genetic material uses this ratio. In fact, if you look at the center rung, or one step on the ladder of DNA, it's one codon rung of the ladder. The geometry of that rung is often modeled as a golden ratio pentagram, stars within stars, where all the ratios are golden mean, and the center bond in the DNA down the zipper is actually, it's called a nonlinear hydrogen bond. It's often been thought of as being responsible for aging. The stability of that bond at the zipper down the slinky is also a golden mean rectangle. And we can see that here where the actual models of how the DNA rung works. You have a pentagonal bond next to a hexagonal bond. And that 5-6 relationship right there, here shown in the guanine cytosine relationship and also in the adenine thymine relationship. These are just how the ladder or the slinky of DNA is braided. And that brings us to the little picture of the slinky. Let's look at the slinky here for a second. See, what happens because your DNA looks like a slinky is the fact that there's a mechanical way to couple a short wave to a long wave. For example, quartz is a slinky. The SiO2, the silicon dioxide helix of the long z-axis optically of quartz, is also a slinky like DNA. Now, the reason Mother Nature uses slinkies in order to teach us about how to connect long waves and short waves is very easy to understand. What happens in a slinky is, here is my hand changing the length of this slinky like this. Okay, that's a long wave. Okay, but as I do it, notice that the sides of the slinky get skinnier. So I have the sides of the slinky getting skinnier like this. See how that pulls in and gets skinnier? while the length of the slinky is a long wave, the width of the slinky is a short wave. And yet these two motions are connected. Long wave, sound, or stricture it's called in piezoelectricity, and short wave, or voltage. So here you have a sound wave, a long wave, connected mechanically because of the slinky to a short wave, a voltage. And that's one of the ways in which Mother Nature uses the slinky shape of DNA to connect long waves to short waves. Well, the fun part of our magnetic X story is that in genetic material, what happens is the DNA is mechanically connected to the sound waves of the heart. So earlier, when we measured the harmonics of the heart, let's look at how the harmonics, or the frequencies of the heartbeat, actually affect this what's called context richness in DNA. In order to tell that story, I need to tell you about a book I read a while ago. The book is called Grammatical Man, Information, Entropy, Language, and Life by Jeremy Campbell. And he is discussing this problem of how genetic material got to be what he called high signal-to-noise ratio, which essentially means that, well, here's the DNA, and it's like millions of times a day taking the RNA, mating it to a DNA codon, and saying, oh, we've replicated, it's like a transistor made an accurate switching. The thing is, the DNA makes this switching operation, this mating of pairs, like sticking two pieces of puzzle together, millions of times a day. And it does it with such incredible accuracy, it's called high signal-to-noise ratio. Well, in this book by Jeremy Campbell, Grammatical Man, he tries to scratch his head and say, golly, how did the genetic material get to be so able to make millions of these information transactions and make so few mistakes? And after lots of fun in the book, he finally decides it's a language problem. It's exactly like if you had a book, and the book was made of letters. And so the letters are like ABC and all these words, and then you had a word within a paragraph, and then a paragraph within a chapter, and then a chapter in a book. Now supposing little Johnny got the book out one day and used his pencil and scribbled out a couple letters, and there were a couple letters missing in the book. Well, the fact is, if you were sitting there reading the book, you'd have so much information about the context that, in fact, you'd be able to replace the missing letters. This is called what he called context dependency or context richness in genetic material. Well, his answer to the question of how genetic material got to be so accurate in making these information transactions was that because there is so much context richness, so much like, well, here's the example he gave. He said, if you were a computer programmer and you were trying to debug DNA, but it was exactly like debugging a program written, let's say it was written in a high-level computer language like C++. Now, in a high-level computer language, you take one instruction and you effectively have grabbed a hold of a block of machine code operations that's huge. It's like a whole nest of operations. So, in fact, if you wanted to debug some fancy program that was making pretty pictures on your screen, and somebody showed you the machine code, this little hexadecimal location that said add to and multiply over here, you'd be like in a swamp of soup that would like mess you up forever if you tried to debug the software using the machine code. So what you have to do to debug a program is look at the context or long chunks or blocks of code. And these long chunks or blocks of code is what we call a high-level programming language, which is basically like C++ or DBase. Well, the thing is, now we've got these genetic engineers today, and they just got so excited, and we congratulate them. It's very useful. But what they figured out is the letters in the code. They don't have a clue what the words mean yet, and they don't even know that such a thing as a paragraph existed. And if somebody told them there's such a thing as a chapter, the only way we discover that level of meaning in the genetic material is this thing called context richness. Now, context richness is the same thing, you see, as this embedding or nesting we just saw the animation about. So when you saw that short wave